Greetings everyone, I am Shubham from Matlab Helper. In this video, I will introduce a one-dimensional heat equation and explore it in Matlab.
Let's start with the mathematical treatment of the heat equation. I will begin with the physical assumptions for the heat equation. I am assuming the specific heat to be sigma and density of the material to be rho. Assume that no heat appears or disappears automatically in the body. Heat flows in the direction of decreasing temperature or towards the cold regions. Thermal conductivity is K. Now let's move toward deriving the heat equation. So consider a heat conducting homogeneous rod that extends from x equal to 0 to x plus delta x with a cross section area A. The temperature between the cross section is the function u x comma t. The amount of heat between the cross section is the definite integral of sigma rho A and u x comma t. These two equations show the rate of heat flowing into the rod and the heat flowing out of the rod. The negative sign indicates that the heat is flowing in the direction of decreasing temperature. The heat change between the cross section is the difference between these two rate equations. To solve the integrals, I am using the mean value theorem. We get the resulting partial u x comma t by partial t equal to a square partial square u x comma t by partial x square. Here a square is thermal conductivity divided by specific heat and density. We have obtained the heat equation as a partial differential equation. Let's solve this heat equation as an initial boundary value problem for the given condition. Let partial u by partial t equal to xx t dash t and partial square u by partial x square equal to x double dash x dt. You might be wondering why I am assuming these conditions, so let me clarify a bit. If you go for the variable separation method to solve the heat equation, then you will obtain the particular solution in the form of u x comma t is equal to xx tt. The solution thus obtained must satisfy the boundary conditions. If you correspond this equation with the heat equation, you will get the reason behind the assumptions. I hope this is clear. Now we can substitute these values in the heat equation to get this result. I can tweak the equation to get this result, which equals negative lambda. This lambda is a separation constant. The tweak that we did earlier will give us two differential equations. For the first differential equation, I have also changed the boundary conditions. Here we will get 3 lambda values and I have written their corresponding general solutions. Lambda equals n square pi square divided by L square for the second differential equation. Thus the general solution obtained is Tt equal to g exponential minus a square n square pi square by L square t. I got the particular solution by combining these two equations where C is this. Now that we have solved the heat equation, let's model it in Matlab.
Before going further, I would like to highlight that only 8.7% of our viewers are subscribed to our channel. If you love our content, then show us your support by subscribing to our channel.
The initialization conditions for the model are shown here. I am using repmat function of MATLAB to make copies of the boundary conditions. This is done to ensure that we get the result for all the points between the boundary conditions. A for loop has been introduced to solve the equation that go up to m's values and calculate the coefficient and the function u x comma t. Note that these code lines written here are only valid for this equation. If you want to model a heat equation with different boundary conditions or any other change in the heat equation, then you have to change the codes under the loop. Now that the model is ready, let's run the program and check our results. The graph tells us that the temperature u x comma t within a thin bar is 0 at the ends. This result satisfies the boundary conditions. Let's rotate the graph. We can see that the heat flows out from the center and goes toward the colder region where the temperature is removed. This is evident because the parabolic shape is reduced as we move away from the hotter region toward the colder area with the increase in time. This again proves that heat is being removed from the ends of the metallic bar. Thank you for watching this video. Do like this video if you found it helpful. If you have any queries, post them in the comments or get in touch with us. Follow us on LinkedIn, Facebook, and subscribe to our YouTube channel. Education is our future, MATLAB is our feature. Happy MATLABing.